and welcome back. In this series, we are slowly building up a 1-bit vacuum tube computer inspired very heavily by the Motorola MC14500, which is a little 1-bit industrial control unit that Motorola built with the original intention of replacing relay ladder logic systems in industrial applications. But we have made a couple of changes to hopefully steer that architecture design to something a little closer to general computing. And the biggest one obviously was that we changed the logic unit to an arithmetic logic unit. And so those changes and the fact that it's being made out of vacuum tubes have led to me dubbing it the UE14500, UE for Usagi Electric. Now, we're real close. We're very close to finishing the processor. There's a big asterisk on the end of that. Most CPUs, central processing units, include some form of program counter, some form of memory, and we don't have any of that yet. And that's because of the way that Motorola designed the MC14500. And that was to have supreme flexibility so that it could be integrated into any system regardless of what kind of memory or program control it was using. And so in the future, we're going to build up our own memory and our own program control and even some input and output for it. But before we get that far, we really need to finish off the processor. And we are almost there. There's just 3 little tiny aspects of it that we haven't built yet. And so what I want to do today is I want to build those 3 parts, and that'll essentially bring the processor to completion. Maybe, I don't think we're going to quite get there because there's a couple other things that I need to tackle and rectify before we power the entire thing up. But we can't fix those things until we build the 3 things that we're missing. So let's hop over to the bench. We'll take a look at what 3 parts of the processor still need to be built. We'll build them up, give them a test, and hopefully that'll get us right up to the doorstep of being finished with the processor. So let's hop over there and get started. All right, so I think you're all pretty familiar with this logic gate diagram. I've been showing this in just about every single episode. This is the logic gate diagram for the entire processor that we're building. And we have built nearly all of this. Moving from left to right, we have the 4-bit instruction register. Then we have the instruction decoder. Then we have the input enable register. And then below that, we have the arithmetic logic unit with the carry register and the result register. And then in the top right, we have the output enable register with the right pin control. So the 3 things that we're missing is the multiplexer control, which is right here. And then on the bottom, we're missing the skip register. And then finally, control for flag F. All right, so we'll just tackle these 3 going from top to bottom. So we'll start with the multiplexer control up here. All the multiplexer is doing is that we want to output the value of the result register onto the data bus during an STO or STOC operation. However, it's very important to note that the STOC operation means that we're outputting the inverse of the result register onto the data bus. Now here I've drawn that as the result register being an input and then an inverter coming off of that input to the other NAND gate down here. But our actual master-slave D flip-flop that we're using for the result register has an output and an inverted output built into it. So we don't actually need this inverter. I just did that for ease of understanding when looking at just the multiplexer. And the multiplexer itself is incredibly simple. It's just 2 AND gates. That's it. Now, due to the weird way that we have to build an AND gate, I've drawn it here as a NAND gate with an inverter, but essentially this is just an AND gate. So if the result register is 1 and we have an STO instruction, both of those inputs go into the NAND gate, pulling its output low. That low output goes into the inverter, which means the output of that inverter is now high. That goes through our OR gate and ultimately to the bus. Conversely, if we do an STOC operation and the result register is low, the inverter means that we have 2 high inputs into the NAND gate, which means that we have a low output coming out of the NAND gate. The inverter changes that to a high output, and that puts a 1 onto the bus, through our OR gate here. Now I have an additional OR gate on the end here with an additional input called EXT. This is so I can essentially force a 1 onto the bus using an external switch. So this is pretty simple. Let's build it up on a PCB right quick. All right, this is the multiplexer board right here. You can see it's super skinny. I managed to stuff 4 tubes on a really narrow base there to make it fit in the limited space that we had, and it actually goes right here. Now I'm only going to secure this with 1 screw because I actually have to remove this to put these pieces in over here. But we're just going to install it temporarily so we can give it a quick test. Okay, I think I've got everything hooked up correctly here to test it. I've got the output of our multiplexer coming across on this really long yellow jumper here to a green LED here, just to show me what the output of it is and hopefully make it a little easier to understand what's going on. Now I have 4 control wires over here. The black one is the result register and the brown one is the inverse result register, and I've got the black to ground and the brown to 24 volts. So that means that our result register is storing a 0. The gray wire is STO, so if I take that high, that'll be an STO instruction, and we shouldn't get an output, and we aren't, which is good because the result register is at a 0. Now if I take that back to ground and I take the purple wire to 1, this is an STOC operation, which should turn our LED on here. Yeah, there we go, check that out. The LED is glowing a nice green. So we're outputting the inverse of the result register, which is storing a 0, onto the data bus, which is awesome. All right, so let's take that back to ground, and now let's store a 1 in our result register by flip-flopping the brown and black wires here. All right, so now if I do an STOC operation, nothing should output. And yeah, all right, so we're still at 0 there, that's good. So if I do an STO operation, we should get an output here. Yeah, check that out, that's working. All right, awesome. So our multiplexer board is working perfectly. That's fantastic. So now let's get back to our logic diagram and take a look at the next thing we need to build. What's important to note here is that the skip register is completely identical to the input enable register, the output enable register, and the 4D flip-flops that we're using for the instruction register. So the really important thing to note here is the data input down here on the bottom, which we have set up as a 3-input AND gate and 2 OR gates. And we have this set up because there are 2 operations that will cause the next instruction to be skipped. There is SKZ and RTN. Now, if an RTN instruction is executed, no matter what, the next instruction will be skipped. However, if an SKZ instruction is executed, the next instruction will only be skipped if the result register is equal to 1. So that's why we have this interesting dual OR gate setup here. You can see that our RTN instruction has an input going into both OR gates, which means that if we execute this instruction, 2 of our 3 inputs into our AND gate will be high. Now, if we execute an SKZ instruction, that only takes 1 input high. The result register has to also be high for both of those inputs to go high. Now, what about our 3rd input into our 3-input AND gate? Well, it's coming from the inverted output of the D flip-flop. And this is because the SKZ or the RTN function will cause us to skip the next instruction. So the skip register is storing a 1 for the next instruction. However, as soon as we store a 1 in this register, the inverted output becomes a 0, which means that we don't have multiple skips happening. Now, this 3-input AND gate and the 2 OR gates have actually already been built and installed on the board, but because we didn't have the skip register installed in the previous episode, we couldn't test them out. So next, all we gotta do is build the skip register on a PCB, put it on the board, and give this a test. All right, the skip register is going to live right here, and that's what this little board right here is. Now you'll notice I've got an additional unfilled space here, and if you remember back to the previous episode, I said that I was going to take the inverse output of OEN and skip and re-invert it and buffer it. And so that's what this little board right here is doing. It's going to take the inverse, invert it, buffer it, and then that buffer output is going to illuminate a little VFD here to let me know whether the OEN or the skip register is storing a 1 or not. In order to get these two boards in, I have to actually pull these boards back out, and that way I can sandwich the whole thing together. All right, I've got the skip register installed up here. I've got my little inverters and buffers and displays here, and then I've got some jumper wires up here set up for control. So right now the skip register and the output enable register are both storing a 0. We can see that because the VFDs here are off. So let's try to store a 1 into the output enable register. So I'll take the brown jumper here and turn it to 24 volts. That's going to be putting a 1 on the data bus. The yellow jumper here is our output enable instruction. So we'll go ahead and take that high. We can see that the output enable register hasn't stored a 1 in it yet, and that's because I need to toggle the clock. So I'll go ahead and toggle the clock right quick. And yeah, there we go. Check it out. So the output enable register is storing a 1 now. So we'll go ahead and turn the OEN instruction off and take our data back down to 0. Next, let's do a skip instruction. The green jumper here is operation 1101. We'll go ahead and take that to 24 volts. We'll toggle the clock. We should see a 1 store into our skip register here. So we'll toggle the clock. Yeah, check it out. So we got a 1 into our skip register. Now, if we take that instruction back to 0, because, well, that's going to be forcing an instruction of 1111, which means that a totally different instruction is going to be coming in, which means the input to this is now 0. So if I toggle the clock again, yeah, there we go. We can see the VFD turned off. So the next instruction after this will now be whatever is next on the program counter. So both our output enable register and our skip register and the control for the skip register over here, as well as our displays for them here, seem to be working perfectly. That's awesome. All right, well, there's only one piece left. That's this piece that goes right here. So let's pull our logic diagram back out and take a look at what that is. Now, it seems weird for us to have special control for FLGF only, but that's because of the way that this architecture executes skips. When we skip the next instruction, we're actually forcing that instruction to be 1111, which is the NOP-F instruction. Now, normally, if we execute the NOP-F instruction, we want FLGF to turn on because we may want to use FLGF to control something exterior to the processor. In the future, we may potentially use FLGF to, I don't know, output serial data to something. So it's important that whenever we skip an instruction, we aren't also turning FLGF on. And this is the design I came up with to do that. Essentially, we have the no operation F instruction coming in on the bottom here. And if everything is normal, when the no operation F goes high, the other input into this final NAND gate will also be high, which will pull the output of it low, which means the inverter will push it high, and that will turn our FLGF on. However, if the skip register is storing a 1, we will now have a 1 coming into this NAND inverter, which makes an AND gate, which means that when the NOP-F instruction comes in, we now have 2 high inputs coming into this NAND gate, which pulls its output low. And then having 1 low input into this NAND gate makes its output high, the inverter changes it to low, and our FLGF does not come on. Now, why do we have this additional inverter coming off of our second NAND gate here, circling back around into the input of that NAND gate through an OR gate? Well, we have this here because the skip register will go right back to a 0 as soon as the 1111 skip operation is executed. So we need this feedback here to keep that output low for the duration of our 1111 skip instruction. Now definitely keep this little inverter and feedback loop in mind. This caused a few problems. So let's pull out the PCB and we'll take a look at the problems that this arrangement gave me and then the solutions that I had to do to fix it. All right, and then our FLGF control goes right here. That is the final piece of the puzzle, and that's what the PC board looks like right here. Now, I did have some difficulties with this one. When I was soldering up, I noticed that I forgot to run the output from this inverter over to the buffers, which meant that the buffers weren't actually outputting anything. So I had to run a jumper wire for that. So I got a little bodge wire here on the back. And then to test the bodge wire to make sure that it was working, I plugged it all in and nothing seemed to be working at all. And in my haste to create a compact board with 8 tubes on it, I forgot to design in the desensitizing capacitors on the input. And so you can see that I've actually gone through and soldered on those desensitizing capacitors on the bottom here. And what this was causing to happen was, if we take a look at our logic diagram again here, is remember we have that inverter acting as a feedback here. And so what was happening was when I would put a signal into the no operation F here, it would cause just enough of a bobble on the input here to cause a bobble on the output here, which caused a bobble on the input here, which caused this to change. And it changed slightly, which caused a bigger change here, which caused a bigger change here, which caused a bigger change here, here, until it was just totally saturated. I needed those desensitizing capacitors to prevent slight changes from causing a feedback loop that caused it to run away and not work. But as soon as I put those desensitizing capacitors in, it seemed to be working. Now I haven't tested it in circuit here, so we'll go ahead and plug it in here and tighten it down with some bolts on there, and then we'll hook it up and see how it goes. Okay, it's like like an hour later. I plugged it all in, I set the cameras up, I started to film, and then it just didn't work. And I was going nuts. The FLGF should be working. I checked it on the bench before and it was working fine. And so I pulled it out and I checked it on the bench again and it was still working fine. So I plugged it in and checked it again and it wouldn't work. And I was going a little nuts, but if you look closely, you can see some evidence of some rework right down here. And it turns out that I had a problem on this connection piece right in the middle. But what was happening was I was taking the minus 12 volts, 24 volts, and ground, and I was splitting them in two, one for the upper rail and one for the lower rail on the FLGF board here. But I got my split messed up. So the upper rail had plus 24, minus 12, and ground in all the right places, but the lower rail had minus 12 volts and ground flip-flopped, so they were in the wrong place. So I cut some traces and did some jumper wires and bodge work here, and it's not pretty, but it should work. I've actually gone ahead and updated the design on the computer, so that way in the future I can recut this center board and recut this one here with the fixes on them, so I won't have this nasty bodge work underneath. On the FLGF board, it's mostly invisible, but it looks terrible on this one, so I really need to recut that one in the future. However, it should be working now. So our skip register here is storing a 0. We can see that because our little VFD here is off. The black wire up here is a 1111 operation. This is the no operation F. So if I take this high, the output out of our FLGF should go high. But if I take this and I make it high, yeah, check that out. The LED is now nice and bright. Okay, so next let's store a 1 in the skip register. So we'll go ahead and set the yellow wire here to 1. We'll hit the clock. All right, there we go. I can see the VFD has lit up. So if I take the black wire high the output for flag F should not change. So let's check that out. Yeah, the output for flag F did not change. All right, so let's toggle the clock one more time. All right, I can see that the VFD here has kicked off. That means our skip register is back to storing a 0. If I take this black wire and go high again, yep, there we go. Our flag F is working perfectly. That's awesome. We are, oh man, we're so close. All we are missing is just the end pieces here and then a connection piece along the top up here. And then, well, that should be it mostly. There's still a couple things that I want to tackle before we actually put this entire thing through its paces. But oh man, we are so close. This is so cool, guys. This is awesome. I can't explain how cool this is. So with just a little bit left to do, I'm gonna keep working as the sun goes down. And in the next episode, well, I hope we should have some pretty exciting stuff going on here. So thank you guys so much for watching. And I really, really hope to see you guys in the next episode because that's gonna be an awesome one. So thank you guys so much.